Welcome back everyone to the Hello World Guide. This is another episode of the SFML3 tutorial series, and in this video we are going to learn about drawing with the SFML3 library, and we are also going to understand what the concept of delta time is and how we can use it and what its importance is. So first of all, let's just go ahead and start by drawing something to our window. So you can see that we have created a render window here, and this basically inherits from window, which is just a plain window. It does not have any drawing functionality in it. So if I go here, you can see it has all of the window functions, but it does not have any drawing functionality. And then we have also got render target, and it inherits from render target, which actually does have drawing functionality. So it inherits from both, so it has both the window and the drawing functionality. So here, for example, this clear function, if I go ahead and open this up, you can see this is coming from the render target. So anyways, if you want to get started by drawing something, we can use the window draw function. So if I do that, we can do window draw, and this basically has a few overloads. So for example, first of all, the first and this the most common overload is that it takes a drawable. A drawable is something like an SFML shape, or we can also make our own drawables. We'll see a drawable in a second. And we have also got one that takes a vertex buffer, which just is a list of vertices for a shape, and then it draws that. And then we have got these, and this is just an array of vertices. So instead of having a typed SFML vertex buffer, this is just SFML vertices in a raw array. Like, it takes a const pointer, it takes a vertex count, as well as a primitive type. This type tells us how we need to draw it, and we'll explore these overloads in a future video. And we've gotten also another one which also takes a first vertex, if you want to draw it with a first vertex and a vertex count. So basically a subsection from an SFML vertex buffer. And all of these also take our render states, but currently we are going to just use this drawable one, which is the simplest one. So to do that, we are going to draw a shape. Now for the shape, we can create a variable here of, for example, an SFML circle shape, and we are going to call this shape. Now this takes a radius as well as a point count. So as you know, drawing perfect circles is not really possible, so that's why we specify a number of points. And if your circle is very small, you can change this point count to be smaller than the default 30, so that it is it takes a less vertices and still looks more or less the same. But if your circle is very large, for example, then you might want to increase the point count so that it does not look jagged and looks smooth. So we're going to set the radius to 50, and we're going to leave the the other thing at default, the point count. And we are basically drawing this here, and if I go ahead and run that, you can see that we get a circle at the corner of our screen. I'm going to first of all go ahead and disable this yellow color. We are going to just remove it, and it is going to clear with the default color, which is black. So now you can see we have got a white circle here, which is the default color for the circle, and you can see that it is appearing in the corner. That is why that is because the coordinate system in SFML and most other graphics libraries and APIs is that the top corner is the top left is the 0 0, or the origin, and then the x-axis increases here and the y-axis increases downwards. And this might be counterintuitive if you're from a mathematical perspective, because usually y-axis increases upwards and decreases downwards, but here it decreases upwards and increases downwards. So if you set this the y value to a negative value, it will go up. So anyway, this is our origin, and for our actual circle, the circle's point of origin is also the top left, which is actually outside of the circle. That is why our circle's center is here instead of being at this corner. Now for games, you often want to have the origin for shapes and objects be at the center, so we are going to set the we are going to use shape.setOrigin to set the origin of our circle shape to whatever we want. Now we can set any origin here, but we want to set to the center. So the default origin is 0 0, which is the top left, and when we are setting an origin, we need to set this relative to that default origin, which means relative to the top left. So we are going to use shape.getRadius to get the radius, which is the midpoint of the circle. Of course, it's a distance to the midpoint, and we are going to set that on both axes. This effectively means that the origin of our circle shape will be set to its center. So now if I go and run that, you should see that the center of the circle is at the top left corner and the other part of the circle is outside. Now we could also change the origin of our window using views. However, we are going to do that in a future video. For now, I'm going to just use shape.setPosition, and we can pass this SFML vector 2f. And if you are coming from SFML2, you might notice an important change here is that for functions like set position, set origin, and other functions that take a 2D vector or a 3D vector in some cases, instead of having an overload that takes a vector and another overload that takes raw values like floats or integers, now there is only the vector overload. So you always need to pass a vector. You cannot pass two separate values in SFML3. So to set the position, we can just go ahead and get our window dot get size, and we are going to actually go ahead and convert that to an SFML vector 2, because that is a vector 2f. We are going to have to convert that to a vector 2f because by default our window size is a vector 2u, which is unsigned integer, it's not float. So after converting that, we can go ahead and divide that by 2, which effectively gives us the center of the window. Since the size, so let me go ahead and actually run that first. So this is basically the 0 0 part. This is 0 on x and 0 on y. X increases here, y increases downwards. So this is the, at this point at the bottom right corner, we have the full window size as the x and y value. And so if you go ahead and divide the window size on both axes by 2, that gives us the center of the window, and now we've got a circle at the exact center. Alright, so now what to do if we want to actually move the circle. So to move the circle, we need to of course take some input and add that. Now input can basically be taken in two ways. First of all, there is an SFML event for that. So if I go ahead and open that, you can see that there is a key pressed event as well as a key release event, and we can take both of these events to see which key was pressed, and we can also get its scan code and other things. So we can go ahead and use that to, for example, when the key is pressed, we can set a flag to start moving, and when it's released, we can reset that flag. But there is also another way, which is to use the SFML keyboard key. We can go ahead and use SFML keyboard if key pressed function, which basically takes a key and it returns whether that key is currently pressed or not. So that is what we are going to use here. So I'm going to go ahead and say SFML keyboard is key pressed, and we are going to say SFML keyboard and we can say key, for example, we can say here A for leftwards motion. Anyways, another thing you might notice coming from SFML2 is that the key here is an enum class instead of just an enum, so you cannot do SFML keyboard A, you have to do SFML keyboard key A. So anyways, we have got this now, and if the A key is pressed, that means we want to move towards the left. So, and to move towards the left, we need to decrease our x value. So I'm going to go ahead and define an SFML vector 2f here called movement, which we are going to initialize to 0 by default. And then when the left key is pressed, we are going to set our movement. We are going to subtract 1 from it to from the x value of this to signal that we need to move towards the left, and we subtract because leftward movement is decreasing. Now for right, we are going to essentially copy this, and this time we are going to increase this because now rightward movement is increasing. We are going to do the same thing for W and S, but of course we are going to use movement.y instead of movement.x here. And for W we need to decrease since upwards movement is decreasing, and vice versa. So yeah, we have got this, and now to actually apply this, we can go ahead and say shape.setPosition, and we can do shape.get position to get the current position of the shape get position, and then we can add to that basically our movement. Now if I go ahead and run that, what you should be able to see is that it moves a bit too fast, but there is also a problem with the way we are moving. So currently we are moving 1 unit every frame. So this every iteration of the while loop, it is 1 frame. We are rendering 1 frame every iteration, and every iteration, if we are holding down the key, we are moving exactly 1 unit per frame. However, the problem is that the time it takes to do 1 frame, which means from the start of this here to the end here, the time here is not really fixed, which means that for example, if it on a faster computer, it will be the time will be less. On a slower machine, it will be greater, and basically, for example, if one PC is running the running 1000 frames in a second and another is running 100 frames in a second, that means our movement will not be consistent across those. So since we are using one unit per frame on the machine that is running 1000 frames per second, that means in 1 second we will move 1000 units, but on the machine that is running at 100 frames per second we'll move in 1 second 100 units, which means it won't be consistent, which is not what we want. We want our movement to be consistent regardless of what is happening, which means whether we are running at a frame rate of 1000 or 100 or any other. So if we want our movement to be consistent, we want to have it be defined in terms of units per second, for example, instead of units per frame. So for that we are going to introduce the concept of delta time. So what delta time is essentially we are going to measure the time it takes to render each frame, and we are going to multiply our movement factor by that time, and it will allow us to basically have a consistent movement regardless of our frame rate, because we are going to multiply by the time it takes each frame, and then our this one will, instead of being units per frame, it will be units per second. So to calculate the delta time, there are two approaches we could take here. We could use the C++ standard chrono library, or we could use SFML's clock library. And since this is a series about SFML, we are going to use the SFML library. So you can of course use the C++ library as well, and the SFML clock library is also kind of a wrapper around the standard library, but we are going to use the chrono one. So we are going to go ahead and make an SFML clock here, and we are going to call this our game clock, or we can just call it clock, and this, when we initialize this, it will start counting the time. Now